Whenever I talk about space to people, everybody's always interested. You know, it's not a boring topic. People are like, oh, that's so cool. Like, black holes exist. Like, wow, that's weird. Like, what? Like, you mean this thing exists in the universe? And it's like, yeah, there are these things that exist that I get to explore and work on. And for whatever reason, humans are just inherently curious. My name is Alec Lancaster. I go to Loyola University, Chicago, and I study theoretical physics and applied mathematics there. And I was working in the high energy physics division at Argonne. The science wouldn't exist if we as humans didn't just ask basic questions like, oh, why am I standing on the ground? Why am I not up in the air floating? Or why am I on this little blue rock in the middle of nowhere that we call the universe? And part of it for me is that it's just inherently interesting. What I've been working on is actually categorizing data for the supernovae that we get from the Dark Energy Survey.
The Dark Energy Survey seeks to take measurements on dark energy and understand the origin of it, the properties of it, why it's doing whatever the heck it does. So to make measurements on dark energy, we don't really know what it is and we don't really know why it exists, and it's also dark so you can't really see it. So how do you make a measurement on it? Well, the universe is expanding and we think that that's because of dark energy. So it makes sense that we would have to try to make measurements on the expansion of the universe in order to make a measurement on dark energy.
So the Dark Energy Survey is a 5-year survey of the southern sky through a telescope in Chile, or through a camera that's mounted on a telescope in Chile called the Dark Energy Camera. It's an international collaboration of which Argonne is one of the collaborators. And what it's doing is that it's probing the universe through several different means. And one of those means is supernova cosmology, to make measurement on dark energy and try to figure out what it is and how it's causing the accelerated expansion of the universe. Supernovae are these intense explosions of stars that are extremely, extremely bright. A lot of those explosions are as bright as the light that we receive from an entire galaxy. They're important to study because there are some supernovae that allow you to make precise measurement on distance in the universe, which is really, really important to try to measure the expansion of the universe and see how quickly the universe's expansion is accelerating specifically. Machine learning is essentially a way of categorizing data. The learning part kind of comes in where you've got data that you want to categorize, right? And you want to make sure that your algorithm is running efficiently and running precisely. So you feed it data that you already know the answer to, and then you check its categorization against your categorization, and you see how correct was my machine learning. And then if it was incorrect or if it wasn't accurate enough, it does it again and adjusts its parameters until it gets to a point that you're satisfied with, essentially.
Given a large sampling of supernovae, you can determine which ones are type 1a by feeding what's called a machine learning algorithm a certain amount of properties for it to test. And eventually, it parses through and creates 2 bins, a bin of type 1a supernovae and a type of not type 1a supernovae. And by doing that, you can separate your samples out into type 1a supernovae and not type 1a supernovae. It's difficult, and machine learning is an arduous process, but it works.
One of the projects that I'm working on is testing these tiny little ring resonators, is what they're called. When we have an earthbound telescope, there's all this noise, light noise in the sky that we have to see through in order to see different things in the universe. So we're working to get these little rings on telescopes to cut out that noise in order for us to see things that are further and further in the infrared spectrum. The Dark Energy Survey is ending pretty soon, actually, and we're going to get that data from them very soon. We have some data, not all of it, so we're going to have basically all of it at some point. And what I've been working on is making sure our categorizations are correct, making sure our machine learning is working, everything is up to its salt, and actually making sure that things are going well. So when we get that actual data, we'll be able to process it. And once we process all that data, we'll be publishing the 5-year sample that the Dark Energy Survey took with cosmological constraints to it. And that is actually going to be the greatest, the single best and most impactful sampling of supernovae in the universe that we've had so far. So that will allow us to make more precise measurement on dark energy and figure out what's going on with our acceleratedly expanding universe. And that's a question that has been just perplexed people for the last 100 years or so. So that's kind of the larger impact. And I've been able to input my own code, my own spin on things as I've gone through this internship, and knowing that I'm just even just a small part of that has been very humbling. My internship at Argonne National Laboratory has been incredible. It's interesting because the people here know that I'm an intern, right? They know that they don't expect my understanding of things to be on their level, because it's definitely not. They have PhDs, I don't. I mean, it just makes sense, right? The work that I've done, I felt the impact on, and I've made impact on the projects that we have going on here. And to me, it's just incredible, because it's only been 10 weeks, and yet I've had this opportunity to make an impact here. And I feel like I'm doing something important, which is just awesome. Being at Argonne gave me the opportunity to explore my own academic interests within where I want to go to grad school, how I want to get connected, and they gave me the tools to be connected to these other places. Like, I had one of the physicists from Australia was like, hey, you should apply to this place in Melbourne. I was like, okay, sure. And like, that was just really cool to me. I mean, you don't get that outside of this kind of setting. People want you to succeed while you're here, and they want to get you connected.